So this is the third Test 2 Solutions video, and we're starting with question number 11. So here we have three parallel current wires, and each are carrying the same current, and I'm going to say that that current is I for all of them, and it's 10 amps. And I also see that they're evenly spaced, so I'm going to call this even space R, which is 2 centimeters, which is 0.02 meters. Oops. And then they all have a length L, which is 50 centimeters, which is half a meter. And so we're asked to find the net force on each wire. So let's take a look carefully at wire 1. So if we look at wire 1, then there's going to be a force on wire 1 due to wire 2 and 3. So let's look at the net magnetic field. Because if we do that, then we can use our force equation and using the magnetic field, because we know that the force is equal to the length of the wire times B times the current in that wire, and then times sine theta, but then in this case theta is equal to, is equal to 1. So we can just say the force is going to be equal to L times B times I. So if we find the net force or the net magnetic field, we can find the net force. So let's look at the net magnetic field. So if we have to look at here at 1, then the force on wire 1, or the net force, is going to be equal to the force on 1 due to wire 2 plus the force on 1 due to wire 3. So if I look at the magnetic fields first. So I'm sorry, I keep going back to force, but let me just go to magnetic fields to cut down some calculations. So B net on 1 is equal to the magnetic force experienced due to on 1, or at the location of 1 due to 2, and the magnetic field at the location of 1 due to 3. So if I look at the wire and I do the right-hand rule number 1, then I see that at 1, the magnetic field due to 2, if I point my thumb in the direction of the current, then I see that it's into the page here, and then this is the magnetic field at 1 due to wire 2. On the magnetic field due to 3, however, is moving to the right. So if I look at that magnetic field and apply my right-hand rule, I see that the magnetic field on 1 due to 3 is out. So overall, they're opposing forces, but one is into the page. The one that's into page is stronger because the distance is shorter. So I know it's going to be the sum of these, and I'm going to define that out is a positive number. So if I look at these net magnetic fields, I look up my equation for a wire way back in my equation bank, and if I look over here, due to a current wire, I see from Ampere's law that V is equal to mu naught I over 2 pi r. So I go over to write that for each magnetic field. So B on 1 due to wire 2 is going to be equal to mu naught I, and they're the same i's in all cases, so we don't have to distinguish I1, I2. B naught I over 2 pi r. And then B, the magnetic field on 1 or at 1 due to 3 is going to be equal to, it's going to be going, and by the way, this one here is, I'm going to say that it's into the page, so it's going to be negative. And then here B is 1, 3 is equal to mu naught I over 2 pi, but in this case, the distance is 2 times r, because it's the distance here is 2r, it's twice as long. So if I can simplify that, pi r. So now if I were to add the net field, then B net on 1 is going to be equal to negative mu naught I over 2 pi r, which is our magnetic field due to the second wire. And then we add this one, which is mu naught I over 4 pi r. And if I simplify that, I end up with minus mu naught I over 4 pi r. So the magnitude of that force is going to be mu naught I over 4 pi r, and then the direction is going to be in the negative of that, so it's going to be into the page. Now if I look at the force on wire 2, then notice that at 2, the magnetic field due to 1 is pointing into the page, and then due to 2, or wire 3, is out of the page. And the distance is the same, so those are going to cancel. So the force on wire 2 is going to be 0. So I might just make a note for wire 2, force due to 1 cancels, force due to 2. And then another thing to notice is that on 3, it turns out that the magnetic field due to 1, it's into the page here, and then also the 1, it's out of the page here, and the distances are comparable. So the calculations are going to be the same as before. And because it's a completely symmetric situation, so it turns out for wire 2, wire 3, it's the same magnitude because the distances are the same. So notice this was missing on here, but if I were to add wire 3, then I would have that it's the same magnitude. And then look here at the directions. Due to wire 2, it's going to be out of the page instead of in is going to be the dominant. So the direction is going to be out of the page. Oh, and we should actually calculate what that force is. So calculate. So if we calculate it, then B net, say on 1, is going to be equal to 4 pi times 10 to the minus 7. And we have in our Tesla meters per amp, and we multiply that, that's our mu naught, and then I is equal to 10 amps, and we have over 4, excuse me, we have 2 pi and then R is equal to 0.02 meters. Okay. I have that, and then what I should do is just calculate directly the force. So remember, the force is going to be equal to L times B times I net. So that's going to be equal to L times mu naught I over 4 pi R, but then we multiply times I, so we're going to get that. And if we were to put all the numbers in and calculate out, cancel everything, then we would end up with 2.5 times 10 to the minus 4 newtons, which would be the final answer. And it's the same for wire 3 as well. In problem 12, we have particles traveling in a uniform magnetic field. And remember, when you have a velocity that is perpendicular to the magnetic field, then the motion is going to be uniform circular motion, because the force is always going to be perpendicular to both B and the velocity. So here we have carbon 12, and it has a charge of plus E. It's a positive charge. And so if we use our right hand rule, point our fingers in the direction of motion V, actually I shouldn't just go over V, but if we go in that direction and then we move our hand, flex our hand towards the magnetic field, which is in the page, then we see that the force is to the left. So the first question actually asked to draw an arrow to show the direction of the initial force. The initial force is at this moment, and it's going to be that direction. Now find the magnitude of the magnetic force on the carbon 12 atom. And so to do that, then we want to use our force equation, which is F is equal to Q VB. Remember that there's a sine theta, but in this case they're perpendicular, so sine theta is 1. So if I were to do that, I put in 1.6 times 10 to the minus 19 coulombs times the 1.50 times 10 to the 5th meters per second that's given, times the 0.20, so Tesla. And if I get that, then I get a force of 4.8 times 10 to the minus 15 newtons. Now if I want to find L, notice that L is equal to twice the radius that we have found. Remember that if we set the force equal to the centripetal force, then we get that the radius of that motion, circular motion, is mv over qb. So that tells us that L is equal to twice. If you don't remember this equation, it's also on the equation bank. So if I were to put those numbers in, then I could find the magnetic field. Finally, it says, or excuse me, the diameter of that motion. So in this case, you would use the mass, which was 1.99 times 10 to the minus 26 kilograms. And finally, the trajectories. Notice that as L increases, as M increases. So the trajectory